we are back for more projectile motion. But now we're going to do things, we're going to complicate things a little more. Before now, we've talked about, for example, the car rolling off the cliff, across the river. And the last one, we talked about pitcher throwing a baseball straight. In both those cases, the projectile, in the first case it was the car, in the second case it was the baseball, were launched horizontally, right? And we called that a zero launch angle, right? But now we're going to generalize, which means we're going to make the case a more general case, and we're going to talk about a general launch angle. Okay, so what does that mean? General launch angle. Well, it means this. Before, our launch angle was 0. Now, the ball or the car might have been launched from an elevation above y equals 0, but the angle relative to the x-axis that the ball and the car were launched was 0. But now we're going to allow for a more general case, the kind of case you've seen before, like when somebody hits a baseball, the baseball goes up. And so what we have here is a initial velocity vector. This is not the path the ball stays on. This is the vector indicating its initial velocity. But as you know, I gotta get myself a sip of water here. But as you know, the ball will not stay on that path. Why? Because it's being accelerated by gravity downward. So, this is a baseball we're talking about. It might have this initial velocity when it actually leaves the bat, but it will quickly be turned downward by gravity. So the trajectory of the ball might be something like this. Okay? The initial velocity was this way, but as soon as the ball left the bat, gravity began working down on it, so gravity made it curve. So this yellow dotted path here is known as the trajectory, and that's the path the ball takes. That's the path the ball follows. That's the path the ball takes. Okay? And so this is the case we're talking about. And it could also be a negative launch angle. We could launch it down. Like if somebody hits the baseball but it goes straight down into the dirt. That would be a negative launch angle down this way. But we're going to take the positive case there. So that's the initial velocity vector. Okay? Inclined an angle theta above the positive x-axis. Now remember, velocity is a vector, so this velocity has components. It has an x part here. This is v naught x. That's the x component of its initial velocity. Its velocity changes, right, as it moves. Its velocity is going to point up for a while, then it's going to point down for a while. So this is only its initial velocity. It has an initial x part here, v naught x, and it has an initial y part here, v naught y. Okay. So these two vectors, the one in the x direction and the one in the y direction, are the components of the total vector. These are not new vectors, okay? Well, they don't represent any new physical quantity, right? They're just the two parts. They're just the two parts, the x part and the y part of the initial velocity vector. And it is these components, v naught x and v naught y, that show up in our projectile motion equations over here. These are the ones carried forth from the last videos. And all these are our three equations of motion written out in the x direction here and the y direction there. And then we apply the requirements for projectile motion, which is the x acceleration is 0 and the y acceleration is negative g. And then you put that 0 and that negative g into our equations of motion, and this is what we get for x, this is what we get for y. And we have v naught y and v naught x here. Those are the same v naught x's and v naught y's that show up all over these equations. Okay. Now what we're going to do is we're going to rewrite these again for the use of, for the general launch. And these are still true, okay, for the general launch angle. We could use these, but they're not quite as user-friendly as if we rewrite them one more time in terms of a general launch angle. And here's how we're going to do that. We're going to remember that last week was all about vectors. We had a vector and we had its two components. So we had the vector v naught and we have its components v naught x and v naught y. And you'll remember that v naught x is v naught times cosine of theta. Why? Because x is the adjacent to cosine. I mean, it's the adjacent to theta, which means x is the cosine. And we also had from last week v naught y is v naught sine of theta. So we're going to make those substitutions. Every time you see a v naught x here, we're going to put in v naught cosine theta. Everywhere you see a v naught y over here, we're going to put in v naught sine theta. Again, all we're doing here is rewriting our equations of motion for projectile motion in terms of a general launch angle theta. That's what we're doing. So we're going to make a substitution. We're also going to make another simplifying assumption. We're going to assume that the motion of the particle starts at the origin. It's a very nice simplifying way to think about it. It makes the equation simpler. Put some zeros into them. We like zeros. I like zeros. I think you like zeros too. I think you like zeros too. Not for grades, okay, but in situations like this. Okay, x0 equals y0 equals 0. So everywhere we see a v naught x over here, we're going to put in a v naught cosine theta. Everywhere we see a v naught y floating around over here in our equations, we're going to put in a v naught sine theta. Everywhere we see an x naught or a y naught, we're going to put a 0. Okay? And here's what we get when we do that. So x naught equals y naught equals 0, and then make these substitutions. And what we get are these right here. These become a new set of equations. They're not really new. They're just written in terms of theta. That's all. Of the general launch angle. Okay. And what we get is we get Vx. That's an x, not a y. Vx equals V naught cosine theta. Right? Because that was V naught x now. Is now V naught cosine theta. X equals V naught cosine theta times the time, right? Because x naught went away. X naught is 0. So the second equation, x plus equals x naught plus v naught xt, becomes this one right here. Vx squared equals v naught squared cosine squared theta. Oh, by the way, this here, when you see that, that is the same as cosine theta all squared. We don't write it cosine theta squared, we write it cosine squared of theta. Okay, we put the exponent right there. It's the same thing. All right, and so for y, we get Vy is V naught sine of theta, right there for V naught y, minus GT. We get y naught goes away, V naught sine of theta t minus 1/2 g t squared. Is that visible? Yes, of course it's visible. And finally, Vy squared equals V naught squared sine squared theta minus 2gy. Okay. So this, was our V. That was V naught x. That is V naught x from the above equations, right? This whole thing here is V naught x squared. This came from V naught y. This came from V naught y. And this came from V naught y squared. And of course, the x naught went away, and the y naught went away. So it looks like a lot. It looks like a big mess, right? We're just making things more complicated. Well, in a sense we are, because we're getting to cases that are more and more interesting with more and more things to think about. So yeah, we're getting complicated, but I want you to remember that these are just the origin of them. They all come from the same place. They're all coming from the same place, which is the equations of motion that we developed way back in chapter 2. Okay, there's 3 equations of motion that you know and love. They're just written here for this application, to apply to this situation here. Okay, so what the next 3 videos, starting I guess on Friday, or whatever day, I think it's anyway, the next 3 videos, I can promise you that, the next 3 videos are going to be applications of these pink equations here, okay, in a situation like this. All right, in fact, I'm going to leave this picture up here, and instead of a baseball, this is going to become a golf ball. So, see you next time when we talk about flying golf balls. Oh, actually, no, golf balls are 2 videos away. I'm so mixed up. Golf balls are 2 videos away. We are going to do, however, 3 videos worth of examples of applications of these equations. So, that's coming up.